So, even though the weather is not very fond of us, as it seems, at least some of us are here, so let's get the show on the road. Anyway, if I seem a bit confused or somehow dizzy, it's because this is my 8th consecutive work day today. I just yesterday came back from a business trip, so I'll try to make sense of this lecture, but let's see what happens. Anyway, software maintenance. So one of the topics we are going to cover today is actually about software development or software development processes. We have been talking on the previous courses about software design and the different ways of developing software, such as waterfall or prototype approaches, but we know that there's also newer models, continuous integration, continuous deployment, so on and so on. So we are taking a look into those things today, seeing what they do and how they affect the way we create software or maintain software, add features, add new content, these sort of things, which are the topics of this course. So, last week we talked about metrics, about different measurements and aspects on observing how well our software or product or service is behaving, or how much work it would require to maintain such a system. The first part of the lecture talked about the requirements for measurement, and if we want to use them in our maintenance process or use them in any sensible way to actually assess what should be done, what can be done, what is affordable to do, because we can't always do everything. These requirements of objectivity, reliability, economicality, and reusability came up on that lecture. So basically, we need to have these fulfilled so that we can have a measurement or metric which is useful for us in the software maintenance or software development work in general. Also, if we want to have some aspects of measurements which combine the things of software quality or the intended quality and the ways to measure them, there's several things in the real, for example, in the standardization. For example, for the software quality, the SQUARE model, which is the ISO IEC 25010, this is full of different ways of measuring things. Also, the testing standard is full of measuring things. The 12207 process model is full of measurements. So it's not about the fact that we aren't capable of measuring things. The problem is that we need to understand what we want to measure. And about this we talked about different things. For example, IBM and HP or these other high-tech companies are focusing on their products. Bit different things really. The HP, which delivers mostly officeware, hardware, laptops, these sort of things, computers, monitors, printers, these sort of things, has different priorities than, for example, Apple, which makes more or less consumer products and things which aim to be as high quality or high luxury quality as possible, whereas the HP things don't necessarily look for that aspect. Anyway, the idea is that you measure what's really important for you and your customer. If you are making, for example, a free-to-play game, you really shouldn't focus on things like transferability or portability, whereas you should actually focus on the user experience, or is the user actually enjoying using your product. Finally, there were also some more advanced metrics introduced, which enables you to identify and assess the problematic modules, which you should probably focus on in the maintenance work or keep an eye on when you are making the first iteration of the product. For example, this cyclomatic complexity, the amount of different ways of completing successfully the module or using the module. For example, here in a flowchart mode, we can see that there's 3 ways of getting things from the start point to end point. These more or less allow us to assess how well off or how realistic or maintainable our architecture in the software will be when it's implemented. Or if it's existing system, what sort of things we need to revise, re-engineer, do some redesign work to maintain or improve the program so that it's actually more maintainable and therefore also lower probability of having problems in it. The other equations, for example, the Halstead equations had a number like that every at least once every 3,000 activities or actions, even professional programmers do errors. So of course this means that we try to keep the amount of variations, amount of complexity, amount of repetition as low as possible. And for example, with the cyclomatic complexity, there was this rule of thumb that if your one module has higher complexity number than 10, you probably should divide that to 2 things or redesign that aspect of your product because it's getting too complicated and it's not maintainable and it's probably error prone and will at one point provide a broken fix. And this is actually also related to today's topic of different continuous models, because the ability to work with these problems is one of the key issues which these continuous delivery and continuous integration model actually tries to give a solution for. So here's the Halstead's software science numbers. So these are more or less for the assessment of different things. How laborious is it to add new feature? How much it will cost? How difficult it will be? What's the level of complexity? How many errors there probably will be in this implementation? How much time we have to reserve, for example, to do the quality assurance work and these sort of things. So today we are talking about the first steps on how the maintenance should be done, or how these different ways of adding features, how the continuous development approaches work. Of course, we have to start with the regression testing, the testing method which by itself doesn't actually mean anything. The regression testing is actually something that's more or less meant as an umbrella term, and including all the testing and quality assurance activities, which we need to do to ensure that our new version of the software, the newest iteration of our product, is something that still works. So, considering this entire picture of what is software system, we can say for example, with the V model, that the unit testing focuses on one component, or that the integration testing is about putting things together, or that the system testing is testing the entire system in alpha or beta stage with the test bed, test environment, or the actual production environment. However, with the regression testing, we really can't say that one thing that it's connected to. It's more or less about doing all the existing testing steps or the necessary testing work to ensure that our fix works. If it means that we change one thing, for example here on this component here, we might want to run the unit tests for that component, or integration tests related to that component, or partial system tests to ensure that the things that this component is responsible for still happen. That's actually one of the problems also in the software maintenance. We know that we have changed some parts of the product or the service, back end, front end, wherever. What do we need to test to ensure that it still works? We don't necessarily have time to fix everything, because we don't also have time to see that everything works. If our test coverage takes something like 2 weeks to complete with all the actual activities with the users or test cases or things like that, or we have low level of automation, meaning that some person has to start doing the testing work when we are releasing new patch or considering releasing a new patch. This is a problem because we don't have 2 weeks. Our customers might wait for 2 hours, maybe a day. If our system is broken for 2 weeks, then we will lose customers and we will lose business. And finally, we will lose everything. So, what do we actually need to test in the regression testing phase? And also, how can we select these things and how can we make this happen even faster? So, this also means that the continuous development model and continuous integration model and these sort of things, which are related to these aspects of shortening the delivery cycle to so small steps that finally we can just throw away 1 day's worth of work or a couple of hours worth of work if it didn't work and do something else. It also means that, of course, it can include all it can be used on all these steps. Of course, you have to understand that usually this continuous delivery or regression testing, we also only talk about these aspects after we have actually released something. So this is something that's usually about software or service or product or something that actually exists. But because the idea is that you always keep something available. If your patch didn't work, then you just don't release it and try something else. Or if we are talking about truly global system, we try roll out the patch, for example, in the European markets or in Finland or in Sweden or somewhere else. If it didn't work, then we just throw it away and try something else somewhere else, like the revision B version in Poland or something like that. If it works, then we just roll out the patch everywhere in all our regions. This also, of course, means that we will be running into version control problems because we sometimes have to integrate different versions together or merge branches in our version control or do these sort of things. But this is a minor problem because even though it is a problem, it's still something that needs to be considered. But anyway, let's keep in mind that we are now actually on this end part of our process if we are considering continuous integration or delivery. The idea here is that we already have a product which we can then offer to someone else. So, as a reminder, also here are the different classifications of what type of maintenance activities there really are. Of course, the additive and emergency activities are more of a special cases of corrective and perfective approaches, but still the idea in all of these different ways of doing maintenance is that it's, at the end of the day, it's a modification. It doesn't matter what we are doing. Are we adding features? Are we making changes to release the software on a new hardware or new platform? Are we doing something to ensure that the system still works? For example, adding capacity like Netflix did on its first major rehaul of the entire architecture. Or are we doing something corrective, just simply making small fixes? It doesn't matter what we are doing here, because in the end we have to do all the quality assurance work, check that everything still works, and we have to ensure that this is true for all the released versions. All the different languages we are supporting, all the different regions we are supporting, or all the different customers we are supporting, if we are selling something that's tailored to their needs. Of course, in many cases we are the systems are the services and applications are built so that they are more or less just the front end on the customer system is just a dummy program which connects to our server system back end somewhere else. So this makes things a bit easier nowadays, because we don't have to send disks around the globe and then send disk telling that, okay, forget the previous disk, just run this and let's hope that you have everything working now. But still, the idea is that you have to do quality assurance work, and you have to know that whatever your patch contains, whether it's corrective actions, preventative actions, adaptive actions, or perfective actions, you need to do testing work. And you should be able to take small enough steps so that you know where the problem came from if it breaks horribly and you are screwed. So, this is taken from the ISO model. It's like I have said many times before, these things really aren't rocket science. So basically everything, even based on that standardization, says that there's always this sort of cycle involved. So there's really nothing interesting here. We have a need, we initiate the process, we do analysis work, we do the design work, we do the implementation work, we do quality acceptance review work, and then on the case of maintenance, decide if we can migrate this to the system, or is this something that we will finally add. Or sometimes we might just say that we are not using this. It's perfectly normal, for example, in entertainment software, i.e. games, to say that, okay, we made this entire patch, we added this more content, we made these and these things, but for example, that the Canadians or Vietnamese people really didn't care for that, the theme is wrong, the new feature is faulty, these sort of things, so other people will never see it. On the other hand, if we are doing some maintenance work on some data management system, like for example these course management systems which every school has. We are currently using WebAudi, some other places are using some other things, but for example we used to have something else called Noppa to manage the courses or manage different things, but that project or that software ran into problem and it didn't really have that good integration with other tools. So instead of actually trying to make everything work, the organization just decided that, okay, this product now comes to end. We could make these things, the problem and modification analysis was done, and some implementations were tried, I guess, but still they decided on the review that it's never going to happen. We are not going to keep supporting this software because it would cost too much, and even though we added some features or added some compatibility, it will never work as well as you would like. So we decided to retire the entire system. Of course, this means that they put the entire system into a bus to the upper state farm, but it also can mean, in smaller scale, that some patches never happen because it's faulty, it's unnecessary, it's something that makes the product worse. And of course, we don't want that to happen. Sometimes we have to do it, but sometimes we can just say that, okay, we are skipping this version and perhaps keep the existing solution so that we can include it in some larger batch, which has to alter how things work. So we can also throw that in if we at that time consider that it's something that's feasible. But what you have to understand is that the continuous integration, continuous deployment, DevOps, all these things, they really aren't things that change anything. We still put the pants on one leg at a time, or we do software by making design, making implementation, making testing work, and then publishing something. It's all only about managing risks and how can we avoid situations where we are taking too large steps so that we don't have time or money to ensure that everything works. So, overly simplified, the continuous integration and such models really don't change how things work. It's small iterations after small iterations after small iterations. It's overly simplified, as mentioned here. We are doing daily patches or daily additions. If it doesn't work, we throw it away and start tomorrow by thinking something else to fix this same problem. If we managed to publish something that broke things, well, then there's even possibility that we can just undo that addition. If we build our system so that it pushes our patches or up-to-date versions every time the users start their software, then why don't we just undo the addition or push to our clients earlier version of the same software? We don't have to tell our clients that, okay, sorry, we kind of screwed up something here. We just add the new version number, which adds the patch, which removes something else. It's not exactly highly ethical. I wouldn't recommend it as a first tactic, but it's business, so of course these things also can hide your doings from bad publicity, and that's also part of doing software engineering work. You try to keep your software or you try to keep your service or application running no matter what, and sometimes if it requires some smoke and mirror tricks, then you probably should be expected to also be able to pull those off. Anyway, this also means that basically the maintenance projects are small projects after the first project. So the first project is the first delivered version, the something that you can always send to your customers. And basically all the maintenance, whatever the type of the maintenance work is more or less just more of the same. But this time we already have something, we already have experiences on what our users might want or how the system behaves when it's out in the real world. So, of course, it means that we have more data to plan changes. We don't have to guess anything. We don't have to estimate anything. We see immediately if something happens. And, of course, it also means that if we have successful addition, we get immediate feedback. And if we have a faulty addition, then we absolutely get immediate feedback. So customers complaining is a fairly good way of getting feedback on what actually broke. So, how do we do that? How do we develop live software? This means, of course, as a live software, that we have something that's constantly sold. Something that's constantly available from your mobile phone app store or somewhere else. Something that's constantly in use with some customers somewhere. Consider that we don't have time or the luxury of taking things offline or saying that, oh, it will be postponed for 1 week because we don't have now enough resources of time to do that. Well, of course, you could do that, but if you start to mess around with your customers, you are not going to be in the software business for very long. But how do we, the idea is how do we actually do these regression testing steps? How do we do continuous integration, continuous delivery, deployment, these sort of things? What are the main ideas behind that? So, of course, if we start with the fundamentals, we make subsystems, we make them a full system, and then we deliver a product. Simple as that. And of course, all these different steps have different activities which are done to them to ensure that the quality is what we might want to have, or at least what we had enough money to test in the first place. So, usually it's not problematic to create one version after another, meaning that we can always just make small incremental step from one version to another by adding one feature, more content, more support, better maintenance, doing some re-engineering work on these modules. But on the integration step, unfortunately, because we also have to be realistic, there's going to be a problem that we actually have in a larger organization, these branches of software development. Also, annoyingly, many times these branches aren't a competition. They aren't test versions saying that at the end there will be only one successful branch, which is now the new trunk, and everyone else follows that. Or that, for example, in this example, that we are testing out the blue and the red and then select one of them and completely discard the another. Of course, this doesn't happen in real life. For example, realistically, we could say that the red one is testing new user interface features, whereas the blue one might be testing out some new solutions for data management or security or these sort of aspects. Of course, this means that both of these things have unique features which we want to have on the main release at some point. So cramming these things together, of course, means that we have to test out different things. And for example, the people doing the red development here have absolutely no idea how this blue version altered the main version of the software. Or, well, they should have an idea. But if it's a worst case scenario, they have no idea how this changed this. So they have no, because they can only see how this version of the main software. So when you are cramming features together, you might end up with interesting conflicts or problems, meaning that you have to spend time and money fixing these issues. So, of course, there's different types of conflicts involved here. Of course, we use version control software because of reasons. These take care of the merge conflicts in general. There's also things done detected by compilers, testing work, code reviews, semantic conflicts, meaning that it's something more inherent than what we can find by simply comparing the systems together. It's not that it's something that's not written in the code itself. It's how the system behaves, and we can see that there's conflict of behavior or irregularities or these sort of things which we have to feed out. And this is actually also what's the main problem behind the regression testing activities. To get rid of these semantic conflicts, of course also get rid of these merge conflicts, but these are things we can more or less see just by using suitable tools to keep our system running. So the idea is that the high idea is that when we are doing additions or integration, integrating two branches together, or doing additions, or doing maintenance work, or doing whatever we are ever doing, the idea is that we don't introduce new faults. Simple as that. We don't introduce new problems. We don't broke something that's already once fixed. Try to keep the re-emergence of faults as low as possible. And of course, one might think that this is given. Why am I lecturing about this aspect? Because statistically, bad fix injection rate is between 2 and 20%, meaning that even with the best quality practices, you are going to at some point provide a bad fix or broken patch or something like that, which creates issues down on the development line. All operating systems, all libraries, all different types of software are susceptible for these sort of things. How many of you have heard that Microsoft released something that broke something? Probably all of you. How many of you have heard that Linux has had a patch that broke something or caused misbehavior? How many of you know that actually when you start to look into the random generator code of several different cybersecurity mechanisms, you find complete bullcrap? And that's because someone forgot to fix the feature or make the additions of using real random number generator or these sort of things. So no matter what you are doing, you are going to at some point make a bad fix. And the regression testing during the maintenance cycles of your work are all the quality assurance and quality control activities which try to stop you before you do something stupid. So, like I mentioned, we don't have money to develop all the features. We don't have time to develop all the features, usually because we don't have money and we don't have personnel. But the problem here is that because we are living in a realistic world, what we can test, what needs to be tested. The systems are large, if we are talking about something that's relatively highly complex piece of software or application or whatever. So we are making one small change. Of course, it doesn't make sense to do all the tests again. If we are, for example, with a car analog, if we are changing the locking mechanism of the front hatch, it doesn't make sense to do the brake tests and all the other things again, because we only made a more change on how the hood stays on the car. Similarly as with software. But the problem with the software is always that we actually, because we don't have standardized parts, or we don't even actually have to accept reality when we are designing software, because there's no inherent size, form, or shape of components or modules or classes. And then what things do we need to test? What a subset of the existing test base do we need to rerun to ensure that things happen? Do we have test automation available? That, of course, is a really nice thing to have. Instead of doing all the things by hand, we just put the unit tests and integration tests and these to happen. But on the other hand, what parts of that we need to change? Because we changed the behavior of our software. What test cases do we need to upgrade or update? Because we know already that something's going to fail, probably because we made things happen a bit differently. This was actually one of the first problems of the test automation tools for user interface. If we recorded something simple, like a robot pressing buttons, and we changed the layout, then we had to do the recording work all again. So that's why also the first and perhaps even the second generation of test automation tools weren't really that great, because you'd have to do constant changes on everything. Now the more intelligent test automation robots, they actually understand what is happening on the system, or they have the model of the system and they aren't physically pressing the button itself. They are invoking the activity of what happens when you press a certain button, which ensures that they can fluidly keep using the software or running test cases on different platforms and different simulations and emulations of the software. Also, the object-oriented problem of cohesion and coupling is one thing that happens here. Of course, we might have documented cases of things how things are connected to each other, what uses what. But if we are using, let's say, inventive approaches on how to implement things, or someone from the group is not following the coding conventions, then we might run up into a problem where the objects really aren't doing what they are telling that they are doing. So many things need to happen, but these are all more or less what happens on the regression testing. So we update the documentation, update the test pool, remove obsolete and harmful cases, perhaps use tools to assess if the cohesion and coupling and these sort of things are still holding the system together. But still, this is only the technical work of doing the testing or doing the quality assurance. If we consider the things from one step higher, for example, from the process point of view, what should we do if we want to develop software more fluidly on the maintenance stage? So here comes the different approaches of doing software development or software maintenance in our course. So, of course, the integration work is the most problematic step. We have to check that the things we changed or additions. Are you asking for a question or? Okay. I thought that you were trying to get a turn to speak. The integration part was and still is the most problematic step of the entire maintenance work. So we made changes, now we have to include them. And we have to update the test cases, we have to update the testing tools, we have to update all these other documentations and things. So how do we do it? So this more or less is the timeline of different approaches. Of course, again here we know that the different process models might not be used as is on any software organization, but these are the ideas or ideals of how things should be considered. There's some things here which you might not personally agree on, or for example consider somewhat ridiculous things, but the idea is that these are again process models or ideas on how things should be done, and organizations should follow at least some of these recommendations. So, the first approach, the Big Bang integration. It more or less was the original way of doing things. Of course, the computers were much more simpler back then, and the world was black and white because colors weren't invented yet. But still, the first idea, of course, is how you do software. You make subsystems, you combine them to each other and integrate when they are ready. And when you are doing some changes, you develop one system, put it to the entire system, make one new subsystem, put it back into the main version of the software. So basically, really simplified approach. Of course, this also meant that the things were done really, really slowly. Of course, the existence of internet has made it easier to access data or transfer things from one place to another, but still the idea is that the problem was that it was so heavily stacking the integration steps to the last stages of the project that if the components weren't that compatible to each other, or they were spec'd a bit differently here and there, the integration stage might took months, years of software projects. And we are not talking about very huge or complex things here. We are talking about the software that needs to be correct, needs to not crash the system, for example. So basically, it meant that, well, this small story here, that the integration step took months. No one really knew how much it still will take, and the project iterations were years. And still problems were left in, because these sort of things were used, for example, surprisingly in the rocket science, on making the carrier vehicles for satellites and these sort of things. For example, the Ariane 4 and Ariane 5 were sort of compatible to each other, but no one actually considered that the Ariane 4 used a different length of float number than Ariane 5 subsystems. So when Ariane 5 made its first test launch, it dived directly into the ocean because the subsystem, which was not integrated correctly, was sending it numbers which it had no idea on what to do with them. So the rocket tried to do a U-turn in the atmosphere, which usually isn't healthy for those things. But anyway, this really isn't a good thing. So let's move towards modern times. So, of course, the development is simple, nothing is changing, but on the other hand, you have huge amount of different things you have to put together, and it's not a good approach. So, then we go a bit further. Microsoft made a innovation, or at least this is what this news item here says. So, make daily builds, make smoke tests, see that everything still works after 1 day of work, or after 1 week of work, or after a certain time of work. So, what can we achieve with this approach? Of course, we know that we aren't going completely the wrong direction. We still have something that sort of works, but still, ultimately, we are just ensuring that we didn't completely break the system apart. We still have to check that the integration and other things work, as was discussed. So, this works, of course, much better than something that's just make all the components ready and then deliver. Of course, here the idea is that usually this integration and smoke tests are done within every few days or every few weeks to ensure that the versions aren't too far apart from to each other, so we more or less know what the idea is. And this is something that was actually taught to me, for example, when I was taking classes in university, because this was sort of relevant back then. So at least once per week, dedicate 1 day or one group of people to ensure that everything still works. You have the capability of slapping the thing together easily or during 1 day, anytime this is needed. So obviously it caused this type of situation. So we have to develop amount of code here, or amount of new code here on the x-axis, and time is on the y-axis. And the difference between these things of the amount of code which is developed and on the yellow the amount of code which is verified, if it's too large, the difference here, of course it means that the risk factor that it becomes costly and messy adventure becomes higher every time the time goes forward, and we do additions without actually integrating things. So this also tries to say that because we started to use daily or weekly smoke and build tests, the preparedness of developing or releasing the new version became much better. There's not as many risks of ensuring that this new patch or new fix will actually work at some point. And also perhaps improved morale, because we now knew that we are doing something which might work. Of course, this is also all about software maintenance, because if we are adding things, we are in danger of running into the problem that something might simply just not work. Okay, so other things that were added to this sort of thinking were more or less that we do timed builds. Each night the system makes a test build. If it runs, it runs. Hooray for us. We allow the system to take multiple hours to do testing work. Of course, this also meant that the test automation started to become a thing. On some places, I know that there was this sort of division where the development work was done during the daytime, and when the night fell, the quality assurance team took over and tested the software throughout the night. Meaning that the developers had a sort of normalish daily routine and normal life, and the testers were the crazy persons who were forced to do work all night because it was much cheaper to just hire people to do testing work than create test automation. Fortunate for you, this is no longer true, but these sort of things have happened. And this is also something which created the follow the sun principle. So when the India develops at one time, the European office is developing when the India is starting to shut down, then it's taken over by the office in the United States, and finally it's developed by Japanese before it goes back to India. So basically the system lives all the time. And for example, the American office is dedicated to testing work, and the Indian and European office are dedicated to development work and these sort of things, which might work quite nicely. But on the other hand, how many of us have money to found 4 offices around the globe so that we can develop and maintain our software? Anyway, going towards the more modern times, so the smoke tests and these sort of things ensured that the small differences were manageable. The showstoppers, the large problems, were still a problem, but still these were at least found out. So we knew what were the difficult integrations, what were the problematic areas, and we could use time to fix these things, even though it might break the cycle a bit. So the extreme programming, which was released around 2000, is actually, it's quite sane and usable approach of doing small development work. Unfortunately, the extreme programming suffered from the extreme case of having a fucking ridiculous name, which meant that no one actually really bothered to understand what the development process is all about. It's not about writing a source code while ski jumping out of an airplane on fire or something like that, which was the first impression given because of the extreme sports and stuff like that, which was a huge trend at that point. So this was mismarketed badly. This is what happens when you put the software engineers to marketing department to give a new name to some approach. But the idea, actually, the continuous integration, daily builds, is actually from here, and it's something that's fairly good and very influential change in the long run, even though at first it was considered a bit stupid thing. So it means that if we are doing development work, no source code or new additions stay unintegrated for more than a couple of hours. You start your day with additions or objectives which ensure that when you go home that day, you either tell that my fix or my addition didn't work, I deleted it, or my addition is complete, I integrated it, and now it's part of the code base. So fairly simple things. Also things about the constant feedback loop of that the developers know daily what they have to do today, how they are going to test it today and see that it works. On the other hand, designers know that, okay, these are the features we are adding this week, these are the features we are adding this month, and these are the things we need to do, and sort of managing that the system floats toward right direction. Of course, with the extreme programming and continuous integration, the problem was at first considered to be that it's fairly reactive way of doing software. So instead of planning quarters or entire years ahead on your software project, deciding on the hardware platform, the software solutions, the tools, the development work, and these sort of things, or the features, you just started to implement things. If you run into scalability problem, then you started to create more scalable version of the existing modules. At least you had the functionalities, now it just have to work a bit better and these sort of things. Of course, this was considered ridiculous, that you are just doing something without knowing what's the end stage is going to be. But on the other hand, the history now has proved right the approach of agile approach, meaning that this continuous integration, where all the code and all the features and all the activities are integrated and the test cases are added. And this sort of approach is actually a very good approach. It also means that if you are integrating something to your code base, you make a couple of tests which ensure that your patch fits seamlessly and it runs in a couple of minutes, connects all the things that you are now working with, and leave the quality assurance iteration for a separate week when you are just fixing or patching away known bugs or problems in the software. And that sounds surprisingly like Scrum, because surprisingly it is Scrum, and that's more or less why or how the Scrum became to be. So, continuous integration. Develop for a couple of hours, integrate your stuff, do testing work, fix the test automation. If it still fails, keep fixing it. If it passes, then start develop a new feature. Not really very difficult thing. Or if you are starting with the test-driven development, that you know that this I have to pass, then develop for a couple of hours, see that you are still passing the tests or that your system still fulfills the criteria. If it doesn't, then you broke something, try to fix it, and see that, okay, now it again passes, and then continue with something else. So depending on if you are designing what needs to pass before we can continue, or how can we ensure that this part fits to the entire system, it's up to the project or up to the design level or sophistication level of the design work or the architecture itself or the existing test automation, but still the general idea stays the same. So, going towards the modern day, the extreme programming stayed with the idea of continuous integration. This added new things like the idea of always fixing the broken builds immediately. If you break the main line or break the product you can deliver, that has to be fixed before anything else is done. You have automated deployment, meaning that you have something that constantly works, and you keep a complete clone of your production environment so that you can check that if it works in the test environment, then it will work on the production environment. This, of course, might sound a bit ridiculous at first, but it also can mean something like that if we are having a cluster of servers as a backend, we have a smaller set of smaller cluster or smaller system with the same principles where we can test out that okay, it still works. Now let's start to add it to the production environment. Of course, I also know that on some companies it's the testing is carried out in the production environment, but because I'm a professional, I can't really recommend that. But the idea is that you keep a exact or as nearly similar clone or small scale version of the production environment that you can always know that this should work, or you don't have, or that you can always have production environment which runs the most recent fixed or working build of the system, and the next version is just coming up when the integration happens and the automation confirms that everything still works. This is more or less the idea of how the continuous integration happens. So commit early, commit often. On commit, the automation takes over, checks that everything happens. If it does, then it's deployed. If the deployment succeeds, then we can start doing the next iteration of the development, or adding new features, or we collect new information or usage reports or customer complaints, or open the next ticket of missing or broken feature or something like that. So this works in development, but this also works in the maintenance cycle. Also, although this is more maintenance oriented. So this also means that we try to keep the manual quality assurance step as small as possible. It doesn't disappear completely. Of course it doesn't. But the idea is that if we have an existing version of the software, and we know, for example, that the usability aspects or the user aspects or the user experience aspects or some technical measurement aspects on this version are good enough or what we want, we can, at certain stages like once a month or when there's too many complaints, check these versions against each other. And this is also where the measurements come in. If we know what we want, we can measure it. If we have a version of the software which is good enough, then of course we can compare it against our newest version to see why these complaints happen, or do we have response times or activities or the amount of required mandatory steps to achieve something still in the same category, in the same ballpark, or in the same level of acceptable. So basically, the idea is that even though we can do that manual work at some stages, the idea is that we more or less create test automation suite. So if you are doing this, you have to start developing at least unit tests or integration tests and these sort of actions, and select your tools so that you can actually do that. If you always have to start doing manual testing work when you are making a small feature addition, then it's not going to work. Because the steps here with these models might be something fairly easy, what you can do in 3-4 hours. For example, fix the Nordic characters problem in the menus. see that all the as and ös and Swedish O characters actually work this time, or these sort of things. It's small changes here and there, but still, how can you ensure that it works? Well, you can run test outputs, or you can, but you'd have to check everything by hand. Anyway, the idea is that you use the test automation to see that or run continuously, so that you can focus on the development work, and making changes to the test base is only a couple of minutes of extra work when you have done the small addition or small change. When you switch for example, with that example, the character coding from some old legacy Windows code page to UTF-8 or something like that. And then just check that every input or output still matches. Okay, so of course, there's some things that we can add to this approach. Of course, the smaller releases are always easier to debug. Also because we have now the networks, we have now the capability of running software somewhere else and just stream it to our mobile phone or our local computer. Let's use that. We can also, by that, revert broken fixes, revert things that didn't work, or we can also select a subset of users who we can test different fixes. If that didn't work, then we can try out something else. Unfortunate for the people of Finland and Vietnam, and I think Canada, we always got the crappy versions of, for example, Rovio mobile games. Because Finland, Canada, and Vietnam were the three test markets which they used to test out problems. So if you were a Swedish person, you'd always get the version of Rovio games that actually worked. Because we were a test laboratory, get the version that crashed down. But still, this is something that's enabled by using these sort of approaches. Instead of pissing our entire customer base off, we could do something that's only relatively small amount of our users will get annoyed with. So the continuous deployment, of course, adds new step here. So in addition of having the development work and the developed code verified, which adds risk of actually having a problematic version, we just release our software when we know that our changes work, and if it didn't work or the customers didn't like it, we can revert it or decide what versions go forward and what not. Of course, it means that the release steps here are added to the picture. And the idea is that the risk between verified and released is basically non-existent. So, continuous delivery means that now, instead of just doing something that we can test out, every version or every iteration should be something that's releasable. So something that we can always release, but we don't actually necessarily release it. If it's not ready yet, or if it's something that we want to further test out, then we can release it later, but still it exists, and it's automatically done to the degree that when we decide that this will go forward, it's just a matter of pushing a button and it works. So there's a sort of a checklist here on how when you are doing continuous delivery, you are doing all these small things. So basically, the interesting part here is the second bullet point, on which you probably, from the viewpoint of maintenance, should focus on. So your team prioritizes keeping the software deployable over working on a new feature, which means that if you have something broken, you always fix that before delivering new things. This, of course, the marketing people might say that this is wrong, you have to remove this. We always are adding new features to keep the customers involved, but the idea here is that we keep the maintainability as high as possible, because we know that if we give away our easily maintainable software, then it's going to be a nightmare a couple of years in the run, because the software lifecycle is years, not months, or not 3-month quarters, like most of the marketing people and the executives of the world seem to think. Anyway, there's some small things. Get automated feedback, do push button deployments and these sort of things, but they are more or less things that you design with an infrastructure. So these are also the things, surprisingly, which I'm emphasizing on your project works, that create a software development environment or infrastructure which actually gives you these options, because these are the options that you are going to need if you want to do something in a feasible way. So finally, the most recent version of this idea of thinking about the integration is the experiment system. This is something that probably exists only the insane minds of software engineering researchers, but basically it means that this push button deployment is used as a basis for doing experiments. We can release different versions of the same software on different places, and then everyone goes to the one that worked most flawlessly, these sort of things. Of course, that might be that's of course possible, and that's the premises of A/B testing, for example, in the user interface testing. But still, I'd guess that if it was used in a large scale, it would annoy the shit out of the customers, who have to get used to all that the system, every time they boot up the system, it's a bit different, because the system they were testing out or experimenting with wasn't actually the one that was selected as the baseline for the future. So this, of course, is experimenting and testing what the customer needs. So instead of adding everything and making the software bloatious and unmaintainable, we experiment that is this what the customer needs. If it's not used, then we roll back. If it's something that performs worse than the previous one, we roll it back, and this sort of approach. Of course, like I mentioned, this is very new thing. There's not that much evidence that how well this works. But for example, at least games industry is into doing this, because the games are experiments, are user experiences anyway. They don't involve your money or your employment or anything like that. So you can do experiments, and if it fails, then it fails. The users aren't expecting a sort of a reliance thing. They want to see interesting new stuff. So on these sort of approaches, it might work. But I'd be very cautious about entering an airplane which was designed this way. So is this feature necessary? Let's try out. We might patch it out before the next flight. But of course, world moves forward, and you have to do experiments at some point. But is it as a part of your development or maintenance work, or how to incorporate it as a limited release? That's what this tries to achieve. So we are running out of time here, but still consider that the delivery activities are with these different continuous what models, something like this. So the waterfall means that we develop, integrate, do quality assurance and production deployment separately. The continuous integration, of course, means that the unit testing and the integration testing are combined to each other. And continuous delivery means that in addition of integrating the parts together or integrating the additions to the existing code base, we also do the quality assurance work to ensure that it still works as so that it can be deployed when necessary. And of course, the continuous deployment means that if it fulfills all the criteria, marks all the things on the checklist, then you can also deploy it without having to do additional work. Whether that's always a good thing or not, then I don't know. And the continuous release, the experimental model, means that the no, it's not a separate thing. But the last model means that you can actually do some sort of experiments with the people and the different deployed versions of the software. Finally, there's a couple of practitioner surveys and a couple of graphs from these, how these things work in real life. Of course, the links are on the video slides, so if you are interested in these things, you might want to go check that out. But we are not going to spend too much time on these things. Interestingly, there's one thing I want to mention from this is this slide about quality assurance work and using different tools and approaches. So keep in mind that this is from 2015. It's not today, but it's still within this decade. So this is sort of relevant information yet. The world hasn't moved on that much from that time. So there's a couple of things in this survey, like the development team manages source code using a source code management or version control tool, and 7% says that they never use anything like that, and these people are professional developers. 12% says that sometimes, less than monthly, we do some additions on version control tools. So of course, this means that the infrastructure doesn't work for them. Someone in their team has the most recent version on in a USB stick or something stupid like that, and when they remember or never add it to some place where it's managed, at least to some degree. Also, the development team or quality assurance organizations uses automated testing to verify quality. Even larger percent of organizations say that this is not something that we usually do, or that we never do anything like that. Some organizations don't even have a common baseline, meaning that they don't maintain a version of the software which is the long haul version, which is used as a basis if the current release of set of patches or additions fail. So things aren't that ready. About 1/3 of the companies are doing things properly. Half of the companies are doing quite well, but still the other half of the software industry is still somewhere where they really can't maintain or further develop their software. They are just one catastrophe away from bankruptcy or writing the entire source code from scratch. So also some barriers. What is the critical barrier for adopting more advanced or refined approaches? Well, no time, surprisingly the most important one. Restricted window for releases due to ongoing business operations, not that surprising either. We got light signal saying that last drinks are out. Anyway, also lack of people with necessary skills, these sort of things. So not really that surprising things, but like I mentioned on the start of this lecture, these things are software engineering and software engineering processes. They aren't anything that you haven't heard before. They are just ways of doing things. So they aren't going to be the silver bullet solving all the problems. Finally, list of the different things. This was done by our the software engineering research group in Aalto, which more or less is one of our fairly common collaborators. They found different things. that were problematic with in the adoption of continuous delivery. And like always, of course, everything affects everything. It wouldn't be software engineering if it weren't. So the product design causes problems for testing, causes troubles for resources. The testing causes troubles by itself, also in integration, and the human and organizational aspects, probably meaning that they don't have anyone who is actually capable of doing the testing work. Okay, so now the lights are gone. We have to stop the lecture before the electricity fails also. But still, these are the benefits of continuous delivery and using these approaches. So, fast release cycles, competitiveness in the market. In the long run, it's actually cheaper to run these things this way, because it's much cheaper to throw away 1 day worth of work than 1 month worth of work when your patch actually didn't work out. And finally, what to remember from this lecture is the definition of maintenance lifecycle, or how the maintenance lifecycle or iteration cycle differs from the software engineering development iteration. It doesn't. That, by the way, is the main idea. And what these different life development models are, what are they trying to achieve, how they differ from each other, and how they try to address the most common problems of software maintenance work. So, finally, remember to register your group. Most of the groups, I think, already have registered, but not all of them. And also remember that you are required to submit 4 out of the 9 weekly assignments which are given each week. There's quite many of you have already submitted at least 1 or 2, but because I don't think it was emphasized enough, I have to emphasize it now, that there is a actually mandatory minimum amount of also those assignments. I will be grading them anytime I have time to actually do so. So that was that about the regression testing and live development models, how we should at least do software development processes while maintaining a live or functioning product or service. So I'll end the recording, and then you can ask questions if you have any.